Here we go with the final lesson for Chapter 4. So these are sections 4.7 and 8. This is all about solving equations using logarithms. Remember, the whole point of a logarithm is to isolate an exponent. So when you're solving for an exponent, that's the time when you would want to involve logs in order to solve. There's kind of two approaches to all of these for how you would want to solve them. You're seeing one common path right here. I'll kind of explain the second. But simply, if you want to solve for an exponent, one way to do that would be to take the log of both sides of the equation. You could use a natural log, or you could just use log. It doesn't matter. Either way would come out with the same result. So if you were to take the log of both sides, as you see right here, remember, one of our properties of logs is that when you have an exponent, the exponent can then move to the front of that log through multiplication, and that's what gets the variable, helps get the variable by itself. So now I can divide both sides by the log of 1.05, and that gets me my solution for x. Notice these are all in 3 sig figs. That should kind of always be the norm unless the directions say otherwise. Same idea on this. I can just take the log of both sides, as you see here. That allows you to take the exponent, put it in front, and then divide both sides by the log of 12 in this case in order to get x by itself. So taking the log of both sides is one common approach. The other common approach would simply be change forms. So if currently I'm in exponent form like this one is, I can just rewrite it into log form. That would also just put x by itself, and then you can go straight to the calculator. So if I were to do that, I would have the log with a base of 1.05 of 200 equals x. And so by putting it into log form, so I would have the log of base 1.05 of 200. I got x on the other side. If you have the newer calculators that can do a log with any base, even ones other than 10, that's a simple way to go, because then you can just go to your calculator, hit math, go down to the one that says log base, and you can put in any log of base of whatever you want. And so that would be another easy way to go. So same idea on this one, isolating the exponent. They took the log of both sides, allows you to put the exponent out front. This one just comes with, so after you divide the log of 3 over to the other side, this one is written in a little bit of a weird form. I'll explain that in a second, but you would just divide the log of 3 over to the other side and then solve for x, where you would add 1 over and then divide by 2. And that would be the easiest way to go. The one potential benefit of doing what you saw here is there's some IB questions that go for an answer like this where it's in exact form instead of rounded. And so it's just good to know how to work with logs and maybe how to rewrite an answer in log form or in exact form for certain cases that may call for that, even though in most cases we will just kind of go for the decimal answer. To 3 sig figs. Moving down, pretty much more of the same. I'm dividing the 18 over first. Then you could take the log of both sides. This is a case where we do tend to use natural logs because you have a base of e. And so that is the common approach when you have a base of e, is to use natural logs. Simply because, remember, this is now right here you have a base of e. This is e. And anytime your base and this number are the same, automatically this is all you have left. And so that's why you see on this left side that the natural log of e is gone, and all you're left with is the power. But then now you could divide the negative 0.1 over and get x by itself. Same idea on this one. Just another case where, if we take the log of both sides, like you're seeing here, for this one, because you have two x's in two different places, this one requires that use of expansion with logs. So remember, anytime you are multiplying, we can break that apart into separate logs through addition. That's one of your properties of logs. A quick reminder on this is really important. Hopefully you're familiar with your formula packet by now. It has a lot of good information about logs in it. So even the properties of logs, like the one I'm using right here, if you didn't already know this, make sure you're familiar with this, but this is your formula packet that you get for all of your tests, and it has some pretty good information with logs. So you have how to change from exponent form to log form. Here you are with your 3 properties of logs that you see right here. So you definitely want to know that those are in there for you, as well as the change of base formula. That's there as well. So keep that in mind. You got some pretty nice tools in there for helping you out on a test. But anyway, we broke that one apart into separate logs. And then just following our properties of logs, remember this is a base of 10, that's 10. So I can wipe out the log of this term and just leave the x minus 1. And now we just continue going on solving for x. So with this line right here, here's kind of the key step. You get all of your x's. So I got an x there, I got an x there. We rewrote it to get our x's on the same side of the equation so that we could factor out x as a greatest common factor. And now I can divide this term over to the other side to get x by itself. So these ones are equations that are already in log form. And so now we are just solving for x. So for these, nicest thing on this one is if you recognize that I have a log base 8 on the left, I got a log base 8 on the right. If this left side is equal to the right side, then I can simply drop the log base 8 from both sides and just keep the x squared and the 4x plus 21, and then you can solve that by factoring. You could also use quadratic formula if you wanted to. Do keep in mind the quadratic formula is in your formula packet, so that's always an option for you. Notice on these, you do get 2 solutions typically whenever you solve a quadratic. Make sure that both are okay to use. There are certain cases, and you'll see this in the next one, where you get a solution for x that doesn't fit if you plug it back in. Remember that you can never take the log of a 0 or a negative. So if in this case in particular, that -3, I'm checking to make sure that if I were to plug it back in, that I'm not trying to take the log of a negative. And in this case we're okay because -3 squared is +9. And if I put the -3 right here, I'm still okay. When I clean that up, I still get a positive out of that. So we're safe on that one. But if you look at the next one, you'll see the difference. Again, here's a case where we got 2 different logs, so we want to combine those into a single log. So in this case, because it was addition, we combine them to a single log through multiplication. So we're multiplying the x minus 6 times x to get this statement that you see right here for line 2. Now we're just changing forms. So it's in log form now. We're going to put it into exponent form. So we have our base of 3 to the 3rd power would equal this. And so that's what you're seeing right here on the next line. So that takes it out of log form and puts it into exponent form. And now we get an equation that we can solve. So here's another case where we just solve by factoring. You get 2 solutions for x. Notice we only kept the 9 on this one. We did not keep -3 because if I put -3 into either one, I get a negative, and you're not allowed to take the log of a negative, so you got to not include the -3. Last couple here, these are just some word problems where logs come in handy to solve. So here we are starting with $5,500 being put into a bank. That is our present value, or the initial amount, or the first term. Either way you want to say that. We have our growth of 4.5%. So that's our base that we're getting for this part of the setup right here. Notice you got the 1 in front because if we are increasing or if we are growing in amount, if I only had a base of 4.5 of just 0.045, and if I did not include the 1, my answers would actually go down over time. So this has to be a value bigger than 1 in order for the results to grow or to increase. Which if you're investing money in a bank, your numbers are going to grow. So we do put the 1 in here. Formula that you would have learned for this back in the past that comes up in Algebra 2 and Math Analysis is your initial amount, and then it's 1 plus the rate is your base. And so that's kind of where this comes from. The other thing that you could link it to is if you look in your formula packet, something we'll be doing also this year is sequences and series. Anytime you are growing by a percent, that always creates a geometric growth pattern. And so if we link this to one of our geometric growth sequences, it's this one right here. So that U1 is our first term, or the starting amount. The R is our rate of growth. And so that's where we're getting the 1.045. And then the exponent represents usually some amount of time or a number of terms. And so this is actually the model that we are following after when we do the setup that you're looking at right now. So something that might help guide you through this. But so back to this, we know the future amount. This is our ending result right here, is the 18,000. So here we are, and just like up above, you would solve this in the same way. Because you are solving for an exponent, we know to use logs. So we're going to divide that 5,500 over first. Then we are going to take the log of both sides. And so that's what you're seeing right here. So after we divide it, take the log of both sides. That allows you to take the x, put it out front, and divide the log of 1.045 over to the other side and get the setup that you see here. Keep in mind, it's always good to recognize how to get certain answers in exact form, because there are going to be cases on tests where they ask for this type of a look for your answer, not always just to 3 sig figs. Sometimes they want some kind of an exact format of your answer. So that's kind of what we're looking at. In this one in particular, notice they rounded the whole thing to an integer, to 27. And because this one said find the number of years after which it first exceeds 18,000. And so this one was compounded only once a year. So this wouldn't occur in the middle of the year. So it would take 27 full years for this to actually happen. So some of these you have to read into just a little bit. Even if that said 26.1, technically that wouldn't occur until 27 full years, because 26.1 would simply mean that it takes more than 26 years. And since they would only compound this once a year, at the end of the year, this wouldn't happen until the end of that year or the beginning of the 27th year. So some of those you have to read into just a little bit to get a proper answer. But when in doubt, fall back on 3 sig figs. But this one is just a more accurate answer for the way this question is stated. Last one here, they give you the formula. This one's simply a matter of just plugging in the numbers. So we have the initial amount, the starting amount. Notice that this one is the same format as this one. You have your initial amount or your starting amount or your first term right here out in front. You have your base. So this one is your base of E. That's your growth rate. Remember that E is about 2.718. So this is already bigger than 1. So we know that these numbers are going to grow based on that, though the negative exponent is going to affect that outcome. So just plugging in the numbers. So our future amount of 250 would go right there. And now we're just solving for t. So divide the 500 over. You would take the natural log of both sides. Typically we would again use a natural log in this case because you have a base of e. So remember right here you have the invisible base of e automatically because it's a natural log. This is also e. So anytime your base and this number are the same, you can just drop the log and just keep the exponent. So you would have just this on one side and natural log of 0.5 on the other side. And then you can just divide this number over to get t by itself.